the Fourier series expansion of a periodic signal x of n is given by x of n is represents it's a discrete time signal, so that is why we are going to deal with a discrete time Fourier series. If I'll take x of n, I'm going to write the definition for DTFS, means Fourier series expansion. X of n is equal to summation where k is lies between n, then x of k e power j into k omega naught n. This omega is represents a discrete time angular frequency. This omega is for continuous time angular frequency. Okay, j into k omega naught n. This is my standard equation where I can represent for x of k also. My x of k is equal to 1 by n summation n is equal to over a period of n x of n e power minus j k omega naught n. Now if I'm going to consider this x of n is my Fourier series expansion, if I'm going to find for x of k, that is inverse Fourier transform. This is the relation for inverse Fourier transform relation. Okay, so that I can write that x of n with respect to x of k DTFS with respect to omega naught. This is your time domain signal and this is your frequency domain signal. This is your time domain signal. Like that, we are going to differentiate the properties we are going to write. First one is linearity. First property is linearity. Take first one, linearity. Okay, if x of n is x of k over DTFS of omega naught and y of n with respect to DTFS of over omega naught with respect to y of k. This is your linearity property. Omega naught is equal to 2 pi by n, 2 pi by capital N. What we discussed in periodic and non-periodic signals for discrete time signal, same omega you are going to get. Omega is equal to 2 pi by n. This is the property for the linearity. If x of n will be given to x of k, y of n it will be changed with respect to y of k. Then z of n is equal to a into x of n plus b into y of n. If I'm going to take it with respect to the DTFS with respect to omega naught, you will get z of k is equal to a into x of k plus b into capital Y of k. This is my linearity function. See, in this module, just they are telling the definition of properties they had given, but in the next module, Fourier transform, there they are asking proof. That is why here we will give definition. We have already solved the problems based on this. In the next module, we are going to prove the proofs for all the properties. Make a note. Make a note first one. Then we'll try for second one. Or Okay, next to take second one, time shift property. Time shift property. If x of n with respect to DTFS, we get x of k, then y of n is equal to x of n minus n naught, with respect to DTFS, y of k is equal to e power minus j k omega naught n into x of k. If I am going to deal with x of n with respect to x of k, we are going to get, but in terms of shifting property, y of n output, x of n minus n naught, if I am going to check, what I am going to get for y of k? Y of k will be e power minus j k omega naught n into x of k I am going to get. This is your shifting property. This is your time shift. Next we have a frequency shift. Third one, frequency shift. Frequency shift. If x of n with respect to DTFS of x of k, then y of n is equal to e power j k omega naught n with respect to DTFS of y of k is equal to x of k minus k naught. If I am going to apply shifting property with respect to x of n or the change in y of k in the time shift, but here it will be opposite. Y of n is equal to e power j k omega naught. If I am going to take, we need to prove y of k is equal to x of k minus k naught with respect to this. This is your frequency domain signal and this is your time domain signal. Next we will go for fourth one, scaling. Scaling property. Here x of n is DTFS of x of k, then y of n is equal to x of p into n, with respect to DTFS. If I am going to apply DTFS for this, y of k is equal to p into x of k over p is greater than 0. Here scaling, shifting, scaling and reflection, what we discussed in the second module, based on that scaling property. Scaling means it's an amplitude with respect to this. With this I am going to get it outside in the output. Y of k is equal to p into x of k we are going to get. This is about your scaling property. These are the just definitions, proofs we are going to study in the next module. Okay, make a note of this. Then we'll take next one, convolution. Okay, next will convolution property. Convolution. If x of n is DTFS of x of k and y of n is DTFS of y of k, then what is the output? Then z of n is equal to x of n convolved with y of n. With respect to, if I am going to apply DTFS for this, we'll get z of k is equal to n into x of k into y of k. What is this n? N is a discrete time signal over a frequency domain. N into x of k into y of k. Or next we have modulation or product property. Next one, modulation or product property. Here, if x of n is DTFS of x of k and y of n is the DTFS of y of k, then output z of n is equal to x of n into y of n. What is the difference between this? This is product and this is convolution. The symbol star represents it's a convolution. This is a product. Don't confuse. With respect to DTFS of z of k is equal to x of k into y of k. Y of k. Next, Parsevall's theorem. Parsevall's theorem. If x of n is DTFS of, for every signal over a omega naught is there, angular frequency x of k, then 1 by n summation n is equal to over a period of n magnitude of x of n whole square is equal to summation k is equal to over a n magnitude of x of k whole square. This is capital X of k. Wherever you are going to get k, you have to write the capital letter. Why? Because this is a representation of frequency domain signal. Okay, next we'll go for second one. Next one, duality. Next property is duality. If x of n DTFS of x of k, then x of n is the DTFS of 1 by n into 1 by n into x of minus k is the property of duality. Next, symmetry property. Symmetry property. If x of n is the DTFS of x of k, then first one, x of n is real. If x of n is a real, DTFS of x conjugate of k is equal to x of minus k. If it is x of n is real. Symmetry, we have a three properties. If x of n is a real, if x of n is a real and even, real and odd, we have a totally three different cases. Second one, if x of n is real and even, okay, we'll get a output with respect to imaginary of x of k, we are going to get that is equal to 0. Then if my x of n is real and odd, with respect to that I am going to get a real term with respect to x of k I am going to get that is equal to 0. These are the three different conditions. When x of n is equal to real, x of n is real and even, x of n is real and odd. These 9 are DTFS, discrete time Fourier series definitions. Can you try for continuous time Fourier series for all 8, 9?
Yes, sir.
Try for continuous time. What is the definition for continuous time signal? The Fourier series representation of a periodic continuous time signal x of t is given by x of t is equal to summation k is equal to minus infinity to infinity x of k e power j k omega naught into t. Have you tried for continuous CTFS, continuous time Fourier series?
Yes, sir.
Sorry? Not tried.
Trying, sir.
See, if I'll get x of t is equal to summation k is equal to minus infinity to infinity x of k e power j k omega naught t. What is the changes? Here x of n replaced by x of t. Here e power j k, this omega and t will be changed. Then where x of k is equal to 1 over t integral over a time x of t into e power minus j k omega naught into t. Why I am going to change integration? Here we are going to replace with respect to x of t. It will be continuous time, so that I am going to take it as a integral. So that if I
Sir, you're not audible, sir.
omega naught linearity. If x of t, if I'm going to take CTFS of x of t will be x of k, and y of t, CTFS of y of t will be y of k. Then z of t is equal to x of t plus b into y of t. So CTFS of z of k is equal to a into x of k plus b into y of k. That is, this is about linearity. Next, what about time shift? There we are going to take n minus n naught. Here you have to take x of t minus t naught you have to take. Then y of k is equal to e power minus j k omega naught t naught x of k you are going to change. Time shift property x of t CTFS of x of k, then y of t is equal to x of t minus t naught. If I am going to apply this shifting, what I am going to get after CTFS? My output will be y of k is equal to e power minus j k omega naught into t into x of k I am going to get. Next, frequency shift, third one. Third one is frequency shift. X of t, same x of t, DTFS of CTFS of x of t will be x of k. Then y of t is equal to e power j k omega naught t into x of t. If I'm going to apply CTFS over a signal y of t, I'm going to get y of k is equal to x of k minus k naught. I'm going to get. In the frequency domain it will not be changed, but the time domain it will be going to change n to t compared to DTFS and CTFS. Now you can try, you'll get some idea. Okay. Scaling, first fourth one, I will write directly z of t is equal to x of at. There I have taken p, here I have taken at. If I am going to apply Fourier series, we will get z of k is equal to x of k. I am going to get, I am not going to get a into x of k, I am going to get only x of k. time differentiation. Fifth one, time differentiation. If x of t over SDTFS x of k, then differentiation of x of t by dt over a Fourier series j into k omega naught x of k I am going to get. Try for another 4. All 5 module notes I have uploaded. Have you seen that?
Yes, sir.
Downloaded everyone?
Yes, sir. Yes, sir.
convolution in time. X of t DTFS CTFS of x of k, y of t CTFS of x y of k. Z of t is equal to x of t convolved with y of t. If I am going to apply CTFS for that, Z of k is equal to t into x of k into y of k. T. There we are going to use n. Here we are going to use capital T. Over a time period we are going to use for convolution. Next we have multiplication or modulation. Z of t is x of t into y of t, or CTFS Z of k is equal to x of k convolved with y of k. In frequency domain we are going to get a convolution. Next, Parson's theorem, P is equal to summation k is equal to minus infinity infinity magnitude of x of k whole square. Whatever we have as energy and power relation we are going to use for CTFS Parson's theorem. Then symmetry property, x of t is real, x conjugate of k is equal to x of minus k. Then x of t is imaginary, x conjugate of k is equal to minus x of minus k. If it is real and even, imaginary of x of k is equal to 0. Real and odd, real of x of k is equal to 0. These are the definitions of Fourier series for both the discrete time as well as continuous time signal. Okay, thank you. We'll continue in the next class.
Thank you, sir.
Thank you.